Hello, guys, and welcome to my channel. In this session, we want to talk about life cycle stages. And if you want to know what is life cycle, well, for a system, we have six stages, which we call it life cycle stages. And this include concept development, production, utilization, support, retirement. And in this session, we want to talk about each life cycle stages in detail. So please join me in this training session and as always, have a good one. ISO IEC IEEE 15288 states a system progresses through its life cycle as a result of actions performed and managed by people in organizations using processes for execution of these actions. Well, a system progresses through a common set of life cycle stages where it is conceived, developed, produced, utilized, supported, and retired. The life cycle model is a framework that helps ensure that the system meets its required functionality throughout its life. For example, to define system requirements and develop system solutions during the concept and development stages, experts from other stages are needed to perform trade off analysis, help make decisions, and arrive at a balanced solution. This ensures that a system has the necessary attributes as early as possible. It is also essential to have the enabling system available to perform required stage functions. This table lists six generic lifecycle stages. The purpose of each is briefly identified, and the options from decision gate events are indicated. Note that stages can overlap and the utilization and support stages run in parallel. Note also that the outcome possibilities for decision gates are the same for all decision gates. Although the stages in this table are listed as independent, non-overlapping, and serial, the activities constituting these stages can be in practice interdependent, overlapping, and concurrent. Consequently, a discussion of system lifecycle stages does not imply that the project should follow a predetermined set of activities or processes unless they add value toward achieving the final goal. Serial time progression is not inherently part of a life cycle model, or stages do not necessarily occur serially one after another in time sequence. One possible example of the progression of a system through its life cycle is shown in this figure. When reference is made to an earlier, prior, next, subsequent, or later stage, this type of model must be kept in mind to avoid confusion by inferring serial time sequencing. Because of the iterative nature of SE, specific processes are not aligned to individual life cycle stages. Rather, the entire set of SE processes is considered and applied at each stage of lifecycle development as appropriate to the scope and complexity of the project. The concept stage begins with some recognition of a need for new or modified SI. Many industries employ an exploratory research activity in the concept stage to study new ideas or enabling technologies and capabilities, which then mature into the initiation of a new project for the SI. A great deal of creative SE is done in this stage, and the systems engineer leading these studies is likely to follow a new idea into the concept selection, perhaps as project champion. Often, the exploratory research activity identifies the enabling technologies. If the work is done properly in earlier stages of the life cycle, it is possible to avoid recalls and rework in later stages. Many life cycle models show the process beginning with requirements or user requirements. In fact, the process begins earlier with interactions and studies to understand potential new organizational capabilities, opportunities, or stakeholder needs. It is critical that in these early studies, a high level preliminary concept be created and explored to whatever depth is necessary to identify technological risks and to assess the technology readiness level or TRL of the project. The focus is on studying potential technologies and determining the state of what is possible and what is not. In some instances, the project may be an outgrowth of research activities where the research engineer or scientist has no connection to a user supported need. The preliminary concept and enabling technologies need to be identified early, and issues arising from the studies need to be addressed during the development stages, according to the National Research Council of the U.S. National Academies. One of the challenges in developing alternate concepts is that we often build on what has worked well for us in the past without considering true alternatives and thereby miss opportunities to make dramatic improvements. This problem has been widely recognized. The preliminary concept will also be used to generate early cost and schedule projections for the project if it moves ahead. Key activities during exploratory research are to clearly define the problem space, characterize the solution space, identify business or mission requirements and stakeholder needs, and while avoiding any design work, provide an estimate of the cost and schedule for the full scale development. Incomplete SE in this stage can lead to poor cost and schedule projections, as well as poor understanding of technical alternatives, resulting in poor trades among the alternatives. For example, the Mars Science Laboratory rover, scheduled for launch in 2009, had to be delayed because of technical glitches. This resulted in missing the launch window, causing a 2-year delay and a 35% cost growth over the proved development costs. Program critics, however, claimed a 400% cost growth based on the early concept studies, and they threatened the project with cancellation as a result. The preliminary concept is a starting point, not an end point. As the project moves into the concept selection activity of the concept stage, the preliminary concept is not put under configuration control, and the key output from exploratory research is a clearer understanding of the business or mission requirements and the stakeholder needs and assessment of the technology's readiness to move to the next stage, and a rough estimate of the project cost and schedule requirements and technical feasibility to first article delivery. Concept selection is the second activity of the concept stage. The concept selection activity is a refinement and broadening of the studies, experiments, and engineering models pursued during the exploratory research activity. The first step is to identify, clarify, and document the stakeholders' conceptual operation of the system across the different stages of use and environments it is to be used in. The operational concept or OPSCON effort should be undertaken to include any changes caused by changes in the manufacture, process, or materials, changes in interface standards, or new feature enhancements being added that can drive various aspects of concept selection of the system. During the concept stage, the team begins in depth studies that evaluate multiple candidate concepts and eventually provide a substantiated justification for the system concept that is selected. As part of this evaluation, mockups may be built for hardware or coded for software, engineering models and simulations may be executed, and prototypes of critical elements may be built and tested. Engineering models and prototypes of critical elements are essential to verify the feasibility of concepts to aid the understanding of stakeholder needs, to explore architectural trade offs, and to explore risks and opportunities. These studies expand the risk and opportunity evaluation to include affordability assessment, environmental impact, failure modes, hazard analysis, technical obsolescence, and system disposal. Issues related to integration and verification must also be explored for each alternate system concept, since these can be discriminators in system selection. The systems engineer facilitates these analyses by coordinating the activities of engineers from many disciplines. Key objectives are to provide confidence that the business case is sound and the proposed solution are achievable. The concept stage may include system and key system element level concept and architecture definition and integration, verification, and validation or IVMV planning. Early validation efforts align requirements with stakeholder expectations. The system capabilities specified by the stakeholders will be met by the combination of system elements. Problems identified for individual system element level concepts should be addressed early to minimize the risk that they fall short of the required functionality or performance when the elements are finally designed and verified. Many projects are driven by uh, eager project champions who want to get on with it. They succumb to the temptation to cut short the concept stage and they use exaggerated projections to support starting development without adequate understanding of the challenges involved. Many commissions reviewing failed systems after the fact have identified insufficient or superficial study in the concept stage as a root cause of failure. The development stage defines and realizes a SI that meets its stakeholder requirements and can be produced, utilized, supported, and retired. The development stage begins with the outputs of the concept stage. The primary output of this stage is the SI. Other outputs can include a SI prototype, enabling system requirements, or the enabling systems themselves, system documentation, and cost estimates for future stages. Business and mission needs, along with stakeholder requirements, are refined into system requirements. These requirements are used to create a system architecture and design. The concept from the previous stage is refined to ensure all system and stakeholder requirements are satisfied. Requirements for production, training, and support facilities are defined. Enabling systems requirements and constraints are considered and incorporated into the design. System analyses are performed to achieve system balance and to optimize the design for key parameters. One of the key activities of the development stage is to specify, analyze, architect, and design the system so that the system elements and their interfaces are understood and specified. Hardware and software elements are fabricated and coded. Operator interfaces are specified, tested, and evaluated during the development stage. Operator and maintainer procedures and training are developed and delivered to ensure humans can interface with the SOI. Feedback is obtained from both external and internal stakeholders through a series of technical reviews and decision gates. Projects that are not showing acceptable progress may be redirected or even terminated. The development stage includes detailed planning and execution of IVMV activities. The planning for these activities need to take place early to ensure that adequate facilities and other resources are available when needed. Well, a source of additional information about IVMV and the significance for project costs and risk when these activities are optimized was the subject of the European Union SysTest program. The production stage is where the system is produced or manufactured. Product modifications may be required to resolve production problems, to reduce production costs, or to enhance product or system capabilities. Any of these may influence system requirements and may require system re-verification and revalidation. All such changes require SE assessment before changes are approved. The utilization stage is where the system is operated in its intended environment to deliver its intended services. Product modifications are often planned for introduction throughout the operation of the system. Such upgrades enhance the capabilities of the system. These changes should be assessed by systems engineers to ensure smooth integration with the operational system. For large complex systems, mid-life upgrades can be substantial endeavors requiring SE effort equivalent to a major program. The support stage is where the system is provided services that enable continued operation. Modifications may be proposed to resolve supportability problems, to reduce operational costs, or to extend the life of a system. These changes require SE assessment to avoid loss of system capabilities while under operations. The retirement stage is where the system and its related services are removed from operation. SE activities in this stage are primarily focused on ensuring that disposal requirements are satisfied. Planning for retirement is part of the system definition during the concept stage. Experience has repeatedly demonstrated the consequences when system retirement is not considered from the outset. Early in the 21st century, many countries have changed their laws to hold the developer of a SOI accountable for proper end of life disposal of the system.